Okay, we're going to go through the first couple examples here on these angular momentum conservation. The first one is just like the demo we did in class, where the student sits on the stool, rotates, mass is in each hand, brings the arms in, extended, so on. So in this one, with the arms extended, the student's rotating at 0.5 radians per second. Now the student's going to bring the masses in. So we should know from the demo and a little bit about conservation of angular momentum that that rotational speed is going to increase. All right, so we're going to solve this problem using conservation of angular momentum. So initial angular momentum equals final angular momentum. Since the object, the student in this case, is rotating the whole time, we're going to go I omega equals I omega. And this will be initial and final. Okay, the inertia is going to be initial and final as well. Okay, so for the initial situation, I'll do that work over here. The initial rotational inertia, we've got the student 1.5, we're given that value, and then holding out the two masses, one in each hand. So that's going to be, the mass is 3 kilograms, and the distance says 1 meter from the axis of rotation, so 1 squared, but there are two of them, so we have to add that twice. So the total initial momentum is going to be 7.5 kilogram meters squared. For the final momentum, we still have the student, so 1.5 plus we still have the 3 kilogram masses, but now they're going in a distance 25 centimeters from the axis, so 0.25 squared plus 0.25 squared. Okay? So the final angular momentum is, we've got 1.875 kilogram meters squared. So you see that's significantly less than the initial angular rotational inertia. So we know that the student will be spinning faster. So let's go back over here. Our initial rotational inertia, 7.5. The initial angular speed, we're given 0.5 radians per second. The final inertia, 1.875, and then we're looking for that final rotational speed. So we solve that equation. We get an answer of 2 radians per second. And that is greater than the 0.5, what the student started with, so that answer makes sense. Okay, now the next example, we have an ice skater sliding 2 meters per second, reaches her arm out, grabs a pole, spins around that, no friction in the system, her arm has no mass, that's kind of weird. What's going to be her angular speed? Okay, so we are going to use conservation of angular momentum. All right, there's no net torque acting on the system, so we know that momentum is going to be conserved. Okay, initially we have the skater skating in a straight line, and then so we want the angular momentum about that pole. So that equation is going to be RMV, that perpendicular symbol. Okay, now once she grabs the pole, she's going to start spinning around it. So that sounds like an I omega, because we're looking for the angular speed. There's our omega. Okay, so for the left side, the initial, the R, says her arms are 0.8 meters long, so we're going to assume she's skating in a line. If here's the pole, here's where she's skating, this distance is 0.8 meters, right there. Okay, so we've got 0.8 meters. The mass, she's 60 kilograms. Her velocity, 2 meters per second. Okay, and then the rotational inertia is going to be the girl going around the pole. So we're going to consider her as a point mass going around that. So that's just mr squared. So her mass 60, and then that radius 0.8 squared. So that answer we get 38.4 kilogram meters squared. and then that's times the angular velocity. That's what we're looking for. So we solve this equation for the angular speed, and we get 2.5 radians per second. And that's our final answer.